Everyone, welcome to this 20th session on Boolean algebra. Today we will discuss some functionality operations, their sets and some different rules required for the next chapter. So let us begin with our today's discussion. Today we will discuss the functionality and the functionally complete sets of operation. Functionally complete sets of operations. Like we have OR, and NOT gates, they form a functionally complete set in the sense that any function can be realized using these operators in SOP or POS form. What is SOP? Sum of product and product of sum form. With the help of De Morgan's theorem, it is possible to produce A dot B using the set of operators, say plus, minus. Likewise, we can develop A plus B by multiplication dot. Now these sets each comprising two operators only, either this or this. These are said to be functionally complete sets. Now again, if we are using NAND operator or NOR operator, it is possible to produce all the Boolean operations. Hence each one of them forms a functionally complete single element set, we can say. So NAND and NOR also we can set. Now let us see what are the Boolean functions and their representations. Now suppose, say a function of n Boolean variables is denoted by, say, f of x1, x2, say up to xn, and another variable of algebra and takes one of the two possible values, either we'll have 0 or 1. The various ways of representing a given function we have to discuss now. So first form, say we are using SOP form, that is sum of product form. So sum of product we have already discussed. Say in sum of product, this is also called as DNF. This is also called as DNF. So DNF long form I'll write, might be useful for objective. It is disjunctive normal form. Disjunctive normal form. Disjunctive normal form. For example, f of a comma b comma c is equal to what we have to do? Sum of what? Product. So here we should have some product involved. So this is sum of these two products. This is product 1, this is product 2. So this is SOP form. Another one we can have the POS form, that is, say, product of sum form. Second form is, say, product of sums form. Now, this is also called as CNF. CNF stands for conjunctive conjunctive normal form. Conjunctive normal form. Now the function in this type of equation may also be written in the form of equation where we are taking product of the sums. So what we have to do, we need to take some product. This is the product, and this product should be of different sums. Say here we should have one sum 1, we can say. Here we can have sum 2. So this should be product of two sums. So this one may be, say, A bar plus B bar, and this one may be B plus C. So this is the format for sum of the product. Now third thing we have to see is that the representation in the form of truth table. So we use truth table to for a specified of listing all the possible combination of values, and we assume that variables and the corresponding values of the functions. For example, suppose we have, we'll consider one function, say f of a comma b comma c is equal to a bar b plus b bar c. So truth table for this we can write as, say, truth table we can write, say, first we can list the decimal code, say decimal code. Then we have three variables, A, B and C. So A, B and C, and there we have some, they are function of, say, A comma B comma C. So we can list out the decimal code. Say we have from 0, 1, 2, 3, 4, 5, 6, 7. So all possible three inputs, how we list out? 0, 0, 0, then 0, 0, 1, 0, 1, 0, 0, 1, 1, then 1, 0, 0, and 1, 0, 1, then 1, 1, 0, then 1, 1, 1. And what will be the corresponding output based on our function? We can list out here the final output. Here we can list out, say it will be 0, 1, 1, 1. Here we will get 0. Here we will get 1, 0, 0. So like this we represent in the truth table form. Now as we have standard operating procedure, similarly we have the SOPs can also be presented in the form of standard sum of product form. Say fourth point we have to discuss is, say, standard sum of products form. So this form is also called as DCF, standard DCF, as we discussed earlier, and it is also called as expanded sum of products form. It is also called as expanded sum of product form, or it is also called as canonical standard sum of product form. Now in this form the function is the sum of number of product terms, where each product term contains all the variables of the function, either in complemented or uncomplemented form. This can be derived from the truth table by finding the sum of all the terms that correspond to those combinations or rows for which function f assumes the value. It can also be obtained from the SOP, like in algebraically form. So say how it will be: f of, say it is function of ABC. So here our normal sum of product is, say, A bar B plus B bar C. So we can expand it to say A bar B, C plus C bar plus BC, sorry, B bar C, A plus A bar. This further we can write A bar BC plus A bar B C bar plus A bar BC plus A B bar C. So now a product term which contains all the variable of the function either in complement or uncomplemented form is called as the min term. It is called as the min term. A min term assumes the value 1 only for one combination of the variable. An n variable function can have all the 2 to the power n min terms. Okay, so the sum of the min terms whose value is equal to 1 is the standard sum of product form of the function. So min terms we denote by small m, say m0, m1, m2, so on. Now these suffixes are the decimal codes of the combination. For a 3 variable term, say m0 will be say A bar B bar C bar, or m1 will be A bar B bar C. Say for this truth table, the min term, say if we have to write for say m0, for this what we can write: A bar B bar C bar, right? So m1 will be equal to A bar B bar C. Then m2 will be A bar B C bar, like this. So these are the min terms. Then what will be m7? M7 will be ABC. So this is, so what we can say, this function ABC we can also represent like, say, f of A comma B comma C is equal to m1 m2 plus m3 plus m5. We can write it in this form also for our previous expression, right? Now another way of representing function, we can represent it, say, function A comma B comma C in the form of min terms, like say 1 comma 2 comma 3 comma 5. Like this also we can represent. Here this summation is representing sum of all min terms whose decimal codes are given in the parenthesis. So whatever is our expression, that we can represent in the form of min terms. Now this is about standard SOP. Now let us discuss about, say, fifth one is standard product of sum form. So this is also called as conjunctive canonical form, or say CCF, or we can also call it as, say, expanded POS or canonical POS. right? Okay, so this is derived by considering the combination for which f is equal to 0. Each term is sum of all the variables. A variable appears in uncomplemented form if it has a value of 0 in the combination, and it appears as complemented form if it has a value of 1 in the combination. For example, the sum corresponding to row 4 in the truth table, say row 4, this is the truth table. Here row 4 we have A bar BC. Say this is row 1, 2, 3, 4. Say this is row 4. In this what we have? We have A bar BC. Or say if we write it in the OR form, it will be A bar plus B plus C. This means wherever A bar is 0, B is 0 and C is 0, this term becomes 0, and being a term in a product, the function assumes the value 0. So sum of products, as in SOP form we have seen min terms. In POS form we will have max term. So in POS form there is a concept of, say, max terms. So a sum term which contains each of the n variable in either complemented or uncomplemented form is called as the max term. A max term assumes the value 0 only for one combination of the variable. For all other combination it will be 1. There will be at least, at the most, 2 to the power n max terms. Okay, the product of max term corresponding to rows for which f is equal to 0. Now max terms are represented by capital letters, whereas min terms were represented by small m number. So max term can be represented as m0, m1, m2 and so on. Now their suffixes denote their decimal code. Say we have decimal code from 0 to 7, that is total 8. Now if we have some function in max term, we can write it as a function of a comma b comma c is equal to, say it may be m0 into m4 m6 dot m7. These are representing the products. Okay, in min term we were representing function as addition, m0 plus m4 plus m6 plus m7. Now this one we can write simply in the form of the numbers, but here in this we use summation in min terms. In max term we will use something like pi. So say pi, this one we can represent as pi of capital M 0, 4, 6, 7. So this is 0, this is 4, this is 6, this is 7. Capital M for max term. So what we have to remember, we have min terms and we have max terms. Min terms related to SOPs, max terms related to POS, min term represented by small letter, POS represented by capital letters. This is represented by summation of m. This is represented by pi m. So these are few points we have to remember. Next session we will see Venn diagram form and the Karnoff map. Until then, have a good day. Thank you.